Okay, hopefully you can see that. It's about as big as I can make it. Okay, from the graphing calculator test and practice test, here's a couple of them that people have trouble with. And then I'll do a few, and then if there's some other ones I'm not getting to, let me know, and we'll go through those. So we're trying to find the derivative here, dy dt, and they're giving us, oh, it's not going to work. Can't do that. Can't make it big, sorry. Okay, and they're giving us, let me rewrite this, you can't see that. Here's y. And they want us to find dy dt. Okay? So this is chain rule problem. Right? You gotta do layers. Now how many layers are there to this problem? Not two. Three. What's the outermost layer? The squared. Okay, so first thing we probably want to do here is we probably want to rewrite this as the quantity cosine of 2 pi t plus 3 squared. Right? Makes it a little easier to see. So how many links am I going to have in my chain link? If there's 3 layers, I'm going to have 3 links. Yeah, one derivative for each layer. Okay, so then let's go do this. What's the derivative? The outermost layer is the power part, right? The square. So what's the derivative of something squared? 2 times something. Right? And the something is a cosine of 2 pi t plus 3. Okay, so we peel away the outside layer. Now what do we got? Cosine. Okay, we have a derivative of cosine. What's the derivative of cosine of something? Negative sine of something. Okay, so times negative sine of 2 pi t plus 3. And then finally, if we peel away the cosine, I get to the very last inside layer. And what's the derivative of 2 pi t plus 3 if I'm differentiating with respect to t? Just 2 pi, yeah. So finally we just get 2 pi. And if I clean this up then, what's that going to look like? Okay, good. That's a time sign. I can take the 2 times 2 times pi gives me a 4 pi out front, right? Negative 4 pi, because I've got that minus sign right there also. So negative 4 pi, and that allows us to get rid of that, and that, and that. Okay? Now what? Looks like I've got cosine of that times sine of that. There's nothing I can do there. I mean, I'm just stuck with those big ugly sines and cosines.
Please excuse the host of students for their field trip to St. Anthony's Hospital. They need to meet in the student parking lot.
Okay, does that make sense? Doesn't make any difference. Now, it doesn't make any difference mathematically. The one thing I would say is you definitely want to have the negative 4 pi out front, because that's a constant. Meaning the sine versus the cosine, no difference. No difference. And they actually wrote the cosine first, it looks like. All right, so let's see. Wrong here. Okay, let's try this one on for size. Okay, this is one of those where, God, it's so small. Here, let me see if I can. see that? Okay, so find the points on this curve where the tangent is parallel to the x-axis. And then they said support your answer graphically, meaning graphically calculate. Yes, just verify. But we don't worry about that. We can do the hard one. We can do this analytically. So what's that mean? Where's it parallel to the x-axis? Okay, where what equals 0? Slope, right? Slope means the slope of a function means what? Excuse me, the derivative of a function means what? Slope. Yeah, the derivative, the value of the derivative of a function equals the slope of that function, right? Yes, I got it. Okay, so then we need to take a derivative, don't we? We want to take a derivative, and if we want to find out where it's parallel to the x-axis, we want to set the derivative equal to 0 and solve. Okay, so we're starting off with y equals 4x cubed plus 6x squared minus 240x plus 21. So what is y prime? And this is an easy one. Right? You just differentiate term by term. 12x squared plus 12x minus 240. Good. And then we're just going to set that equal to 0. And I say this tongue-in-cheek, but really what you're doing is you're posing a question here. Maybe it's not technically a math guy, but we'll say so. You want to know, by setting that equal to 0, I'm asking the question. The only variable up here is x. And so I'm really asking the question, for what values of x is this equation true, right? Now, this is a graphing calculator test, so can anybody give me an idea how I might save a little time and sidestep the algebra here? Say it again? Yeah, okay, it's quadratic formula we could use. We could graph the thing. You guys have that fancy polysmalt. You know about, I showed you polysmalt, right? Yeah. Or you have, what do you guys use all the time? Aqueduct. Okay, you got all kinds of plethora of choices here. Take your pick. Yeah, honestly I think the fastest way, well, probably it's poly simultaneous, polysmalt. So if we do that, apps alpha p skips you down. Where's p? I can't read that. So right there. Okay, so I want poly root finder. And what's the order? 2, right? That's the highest degree, highest power is the order of the polynomial. So it's 2, real, looks good, everything looks good. Next. So a sub 2, 12. Everybody know where you get this? Apps? You don't have it? You sure? Is anybody, who doesn't have it? Oh, well, you need to have it. I'll give it to you. Okay, this is a good one to have. You don't have to use this one. You could. Does everybody have aqueduct for an alternative? Okay. But I will get this one for you. This is a good one. 12, and then negative 240. Solve, and there we go. Okay. Negative 5, positive 4. Make sense? Okay. Questions? All right. Oh, and it wants the points. Okay, so we found x, exactly. Pretty easy to find y, isn't it? Okay, now, how do we find, there's a little trick on here, though. While we're at it, talking graphing calculator stuff. How could I find the value of the polynomial? Okay, I'm going to quit. How how can I find the value of the polynomial? I mean, I could just plug it in. Here's a little trick though. If I can plug in, if I have to evaluate, in this case it's not that big an advantage because I'm only really evaluating it twice, but if I have to evaluate a function multiple times, there's a couple good shortcuts you can take. Let me know how can I save a little time here, be efficient? If you can learn to use these calculators efficiently, oh man, that's, for college that is priceless. Seriously, that's, not only in math, but in your chemistry and physics classes, it's just huge. Okay, here's one little trick. No go?
It's after first.
Okay. You can enter the function in terms of x, and then I can just store values of x and evaluate the function and without having to retype the whole thing. So I'll go back here. I got this thing ready to go. Okay, so there it is. There's my original function. So we can just put in 4x cubed plus 6x squared minus 240x plus 21 and hit enter. Okay? And it's going to give me some nonsense number. And the reason it's doing that is because there is a value of x stored in there from some previous problem, who knows when. And we don't know what that is though, so we'll ignore that number. But now I want to know what the value of this function is when x is, what do we say, negative 5 or 4?
Yeah.
So I'll do this. I'll go negative 5, stow for store as x, enter. And it's going to say negative 5, so that's the current x value. Now if I go back up and grab this expression and hit enter, 871. There's the value. How about that? Say it again. This is the y value. This is the value of that expression when I've set x to be negative 5. Okay, now if I want, so there's now the nice thing is they'll both be on the screen. I can go put in positive 4. I can just say 4 store as x and just go up and grab it again and hit enter to evaluate it, and I get negative 587. So they're both right on the screen there. Okay. Make sense? Now there's another trick. This is even a trickier trick. If I put this in, if you had to do a lot of these, let's say I had to do 10 or 11 of these x values, even this would get a little bit time consuming. I can go to y equals and clear everything out. I think this is right. I'm not going to embarrass myself. I think this will work. If I put this function in as y1, I'm not going to graph it, although I could. But then I got to mess with getting the screen the right size and everything. So 4x cubed plus 6x squared minus 240x plus 21 and hit enter. Okay, now what I'm going to do is I'm going to go to the table and let it generate a list of values for me, and I can quickly just navigate through that table to find the x values that I want and the corresponding y values. I don't really have to do this, but I'm going to show you how. If I go second F2, I go up to table set. I can do some things like determine where's the starting value of the table, and here's an important one, delta table. What do you suppose that is? Okay, yeah, that's the step size, incremental size between the x values. Well, we just want integers here, so I would make it 1. So I'm going by ones. And I'm going to go ahead and start my table at negative 10, how about, this time. And so now if I just go second table, look what it does. Okay, it gives me, for all these x values, it's going to give me the corresponding y values. And so if I needed to find a bunch in a hurry, well, there's my negative 5,871. I can just navigate down, quickly navigate down through this table. And there's probably even a way to page, I don't know what that is, but if you look, I'm sure you can find it. So I get a whole list of these values, right? So if I needed to do a whole bunch of them, that's a great way to do it. Okay? Make sense? All right. What else? Okay, tell me if this is one we want to do. I'm not sure. I just kind of picked these based on. Is this a good one? Sure. Yes. Make sure this is one we want to do. Should we skip that one for now, or is that? How would we do this one? Product rule, and then I'd have a chain rule right here, wouldn't it? The second factor in that product would require a chain rule. So, yeah.
I just have one question on that.
Yeah.
When you expand it out, they always times the column. Like you expand it out, it would be like 8 in front of 2x.
Okay. Well, maybe we should do this one. Let's do this one. Okay. So if I'm going to differentiate this, product rule just tells me what?
Derivative times normal plus.
Yeah. Okay. Good. So factor times derivative plus other factor times other derivative, right? So we could do something like x cubed times the derivative of the second factor. Now, what's that going to do? Okay, good. So I've got two layers. I've got hand to the fourth. Derivative of hand to the fourth is okay. 4 hand cubed. Okay, good. So there's first times derivative of the second plus second.
You have to go one more chain.
Oh, whoops, I'm sorry. Gosh, yeah. Forgot the second layer. Okay, sorry about that. So what's the derivative of the inside? 2, there we go. Yeah, you probably, my phone's on. Sorry, I got a potentially sick kid today, so I got to leave it on. Sorry about that. Second times derivative of the first would just be 3x squared. Good. Okay, so now, yeah, there's something that does come up here, and I have an algebra issue, and we'll be doing a lot of this for the rest of the year, problems like this. I could expand this out, but I don't really want to. I'd rather just factor this. You see common factors in both of those two terms. Okay, good. So I've got some like bases here, don't I? I've got the like base x there and there, right? And I've got the like base, the quantity 2x minus 1 there and there. I can factor both of those out. And I can probably even factor out, well, that's all I can factor out. Yeah. Okay, so let's do that. Let's take out the biggest common powers of both of those bases. So that's going to give me an x squared. Now, the biggest common power means the smaller of the two, right? Okay. I can take an x squared away from both of those, but I can't take an x cubed. That one's only got an x squared to give, right? So x squared, and then what's the biggest common power of my 2x minus 1 base? Cubed, okay? And then what's left? Okay, so when I take those away, let's see what's gone. So I took away 2 of those, and that's a good way to show your work notationally. See what I did? I factored out 2 of those, leaving me with 1. And here I factored out all of those, so it divides away. Here I factored out the whole thing. Here I factored out all but 1 power. Okay? So from the first term, I'm left with 2 times 4 is 6. 8, or 8. In this universe, it's 8, I guess. 8 times X, right?
Quantity, you can do X, big O.
Okay, times 3. There we go. Okay, and I can do some additional simplification. I can take everything inside the brackets and distribute the 3 and combine like terms, and then I'd be done. So I've got my x squared times the quantity 2x minus 1 cubed. When all the dust settles there, what am I going to get? How many x's? 14. Minus 3. Yeah, there you go. And there's a temptation among smart, overachievers to want to expand that out, but we really don't want it. We don't want it because ultimately we're going to want to have these things factored, which you're going to, and next chapter that's going to become abundantly aware to you why we want that. Well, we're going to do just a little quick peek into our futures. We're going to be, most of the time, high 90% of the time, when we're taking derivatives, we're trying to find horizontal tangents, and so we're going to be setting them equal to 0 and solving. And to solve equations, we want to have them factored. So we can set the factors equal to 0, right? Zero product property. So we're going to want them factored anyway in the future, so that's a great answer. Okay? Make sense? All right. Okay, some physics. All right, sounded like this was something we needed to do. All right, so yeah, I shortened this just a bit so you could read it. So we got equation for free fall at the surface of some celestial body in outer space is this. Okay, now it's really better to write this as S of t, especially with physics stuff, because it reminds us that position is a function of time. This is the independent variable. You don't have to, but I mean that's really, in physics, that's a good habit to be. So we want to know then, how long does it take the rock to reach a velocity of 25.9 meters per second? Okay. Well, we don't have a velocity function up there. How do we get a velocity function from a position function? Derivative. Okay, good. So we know that v of t is just s prime of t, right? That's our derivative. So what is that? 2 point, say it again, 3.44. T, okay? There's our velocity function. If we want to know how long it takes the velocity to reach 25.9, what do I do? Say it again. Okay, good. So we're going to, for s prime of t, right? So we're going to set velocity or s prime, same thing, equal to 25.9. So that amounts to this. We're just creating the equation. The velocity function, right? Velocity equals 25.9. I'm solving for t. Okay? Right? All right. You tell me if you want to do this one, or is it, or we want to do another physics one? This one, okay. Okay, so now this looks like what's gonna be what's this looking like? Okay, it's looking like a quotient, but is it really? No, it's not. We can avoid, and this is really important, we want to find an equation for the line tangent to the curve at x equals 1. We can avoid having to do the quotient here. How come? And try to articulate this. Choose your words carefully. How come this is not a quotient problem? Okay, the 8's a constant. I can pull the 1/8 out front. That's no big deal. But because I've got an x to some power of 1 on the bottom, I can divide this up into separate fractions and just have each term in this sum be a power of x. I'm just using the quotient rule for division of like bases, right? If I divide some power of x by some power of x, I just subtract the exponents. Now, if the bottom had been something like the 8 times, well, what if it had been 8 times the quantity x plus 3? Then we're kind of stuck, right? Then we'd have to have like bases on the top in order to do that trick, and unfortunately we don't, right? Although, at the very end of the year, that's a really sneaky trick for doing integration. We're able to actually do some finagling and take advantage of that trick later on. So hold that thought for several months, and then we'll get back to it. And here's another thing I want to point out right up front. When you see a problem like this, I want you should start to smile. When you write an equation for a tangent line, if I'm going to be evaluating the derivative at, say, x equals 1 in this case, is there any need for me to spend time making the derivative answer, look all pretty? How come? You're right. I'm just going to plug a value in and I'm going to evaluate it anyway. I'm just going to plug in x equals 1 into my derivative. And it's a lot easier to simplify numbers than variables, right? If I put a 1 in there, it's very simple to get a numerical answer out. So don't spend time, making this thing look all pretty and simplifying when you're just going to evaluate it anyway. Okay, so first things first, though. So let's go ahead and rewrite this function. I've got y equals, starting off with x cubed plus 1 over 8x. What am I going to do to make this a non-quotient? Because the quotient rule is a little bit messy. Pull the 8 up front. And then say it again. I got rid of the 8. Split it. Okay, good. So I got x cubed over x, which is x squared, okay, plus 1 over x written as a power. So x to the negative 1. There, much easier. Now I can just differentiate term by term and just use the power rule. Okay. So y prime is, we'll leave our 1/8 out front. Derivative of the first term, x 2x. And then derivative of the second term, okay. So if I wanted to rewrite that a little bit, I could say 1/8 times 2x minus 1 over x squared, right? But all I'm really trying to do is find the equation of a tangent line, right? And so I need a point and a slope. The slope is going to be what? Plug in x, yeah. So the slope of the tangent line is just equal to y prime at x equals 1, right? So the slope of the tangent line would just be 1/8 times 2 times 1 minus 1 over 1 squared. Oh, what's that? 1 times 1/8, 1/8, right? So there's our slope of the tangent line. And now this is no longer a calculus problem. Now this is just an algebra problem. We want the equation of a line. We got a slope. We need a point. How do I find the point? Good. I'll evaluate the original function at 1. So that's going to be 1 cubed plus 1 over 8 times 1. What does that give us? 2 over 8? 1/4? So that means that my point is at 1/4, and my slope is 1/8, right? And so now it's a piece of cake. Now I need to find B, don't I? I know M, I just need to find B. So this goes back to algebra 1. Now, of course, you remember, if I want to solve for a quantity in an equation, I have to be able to evaluate everything else, plug in values for everything else. So I can, what was Y? 1/4. 1/4 equals 1/8 times 1 plus B. So it looks like B is going to be 1/4 minus 1/8, which is 1/8. Okay. And our answer is just Y equals 1/8 x plus 1/8. Very good. Okay. All right. Okay, that's all I had picked. Any other ones? The other. Now I'm kind of depending on people that have done the practice stuff. Are we about out of time? Is that? There might be. Let me look and see if there is. Oh, okay. Okay, that'd be a good one. See if we have time to get through at least part of that. All right, let's see. That must be. That guy. No, it's not that guy. Let's do. Oh, okay. You know what? I see one on here. Okay, this is a little, I don't know if I want to do this. There's one on here I probably need to take off. Did anybody get the marginal cost one? Okay, yeah, that shouldn't be on here. We'll do that stuff, but we're not quite ready for it. That's going to be chapter 3. I'll make sure that one's not on here. We'll be in here. Oh, in fact, that one's not on it. Anyway, so never mind. Is this the one? Projectile motion? This is the one. I think this is the one you're talking about, right? Is that it? Okay. All right. Well, let's just talk about it. We won't be able to get through the whole thing. So if we've got this position function here. S equals 42t minus 0.7 t squared. Now, it wants to know some things. It says find the object's velocity and acceleration as functions of time. That's easy. Velocity is what? Derivative of position. Acceleration would be derivative of velocity. So just differentiate twice to get that. It wants to know how long does it take the object to reach its highest point. Now, what's going to be true when it reaches its highest point? Velocity is 0. There's really two ways you could do this. I could find the maximum of, and you have a graphing calculator. I could graph the position function and just ask the calculator what the maximum is, which my calculator does. Or even easier than that, I could take the velocity function and set it equal to 0 and find when the velocity is 0. And that's got to be when it gets to its highest point. Velocity goes from positive to 0 to negative, right? Okay, what about how high does the object go? Well, if I know the answer to B, if I know the time it takes to get to the highest point, plug it into position function to find the height, right? When does the object first reach half of its maximum height? what would I do there? Now, if I know the answer to B, actually, no, never mind. If I know the answer to C, if I know the maximum height, say the maximum height is 100.
No, divide it first, and then you divide it.
Okay, if I know the maximum height, let's say it's 100, then that means that half the maximum height is 50. So I would plug 50 in for S and solve using my graphing calculator, right? Okay, how long is the object aloft? Now, if I know the answer to B, how long does it take to reach its highest point?
Half of it.
That times 2. And it takes that long to get up and that long to get back down. Tricky, huh? Okay.